In this lesson, you will learn to factor the difference of perfect squares. You will follow the rule for difference of perfect squares in order to write it in factored form. In order to do that, you will take the square root of each term and write it in this factored form. So let's first make sense of the factored form. If we have a plus b and we multiply that with a minus b, using the distributive property or even the box method, we can multiply this back together. So we'll do a times the a minus b and b times the a minus b. If we notice a times a gives us a squared, a times negative b is negative ab, b times a, we'll write that as positive ab so that we can combine our like terms, and then b times negative b is negative b squared. So if you'll notice, your like terms will cancel. A negative 1ab and a positive 1ab will leave you just with a squared minus b squared, which is the format for the difference of perfect squares. We know that that's the difference of perfect squares because there's a subtraction sign, which means difference, and each term must be perfect squares. So let's look at our first example. For our a term, we'll take the square root of the 144x squared. For our b term, we will take the square root of 49. Be very careful not to take the square root of negative 49. Because that is a subtraction sign, we can follow this rule of factoring the difference of perfect squares. Just take the square root of the term 49, not negative 49. So the square root of 144, hopefully you recognize that as a perfect square, is 12. The square root of x squared is just x. If you need to do prime factorization to find the groups of like factors, feel free to do that as well. The square root of 49 is 7. That again is a perfect square. So in order to write it in our factored form, we take our a and b terms, writing them each in our parentheses. So a, b, where we have a plus and a minus sign as our factored form shows. You could also have this answer as 12x minus 7 and then 12x plus 7. So the order of the factors do not matter as long as you have one plus and one minus in that factored form. Let's take a look at another example. Again, we notice this as the difference, and these are both perfect squares, so we can factor it using the rule. So our a term, we'll take the square root of the x squared. For our b term, we'll take the square root of 225. The square root of x squared is x, and the square root of 225, that is a perfect square, and it equals 15. So again, we write it in our factor form using those terms. We have x plus 15 and then x minus 15. And that is it. You can distribute this back together to check that it equals the original problem. Let's take a look at the next one. We should first notice that this is a plus sign. So it actually does not factor in the same form as the difference of squares, but let's pretend that it does. So if we took the square root of 4x squared and take the square root of 25, we get 2x and a 5, and if we write the plus and minus sign, well, that is the factored form for the difference of squares. So because our problem has a plus sign, this is not the factored form for this problem. Well, what if we had both positives? So, sorry, not 4x, but 2x. 2x plus 5, and then another 2x plus 5. If we were to actually use the distributive property and multiply all of this together, you would find 4x squared plus 20x plus 25. You'll get the 4 terms by distributing, and when you combine those like terms in the center, it equals this trinomial. So again, we notice it does not equal the same. We have the first term 4x squared and the last term 25, but it's that middle term that we needed it to cancel that it did not happen. So I always have to look at all the options. What about 2x minus 5 and 2x minus 5? So again, if you distribute that out together, you'll end up finding 4x squared minus 20x plus 25. So once again, that is not the factored form. So looking at our note here, the sum, so there's a plus sign, the sum of perfect squares is not factorable. We call these problems prime. So recognize as soon as it has a plus sign with perfect square terms, your answer would just be prime. So let's look at one last problem. We have x to the fourth minus 256. Again, we should notice this is the difference of perfect squares. Each of these terms are perfect squares. So we can take the square root. If you'll recall, taking the square root of x to the fourth, if you need to, write out those x's and see that we have 1, 2 pairs, because our index number is an understood 2. So 2 pairs of x's would be x squared. So the square root of x to the fourth gives us x squared. The square root of 256, this is a perfect square, it equals 16. Feel free to use prime factors and look for your pairs of factors if you need to do that as well. So let's write the factored form. We have x squared plus 16 and x squared minus 16. But we're not done here. We just talked about the sum of perfect squares. This part is prime. But then other factor, the difference of perfect square, this one is still factorable. So I use my abbreviation. This is the difference of perfect squares, and we must factor completely. So for our final answer, we are going to bring down the sum of perfect squares. We do not call this entire problem prime. Just this part, the sum of squares, is prime, meaning it is not factorable any further. But the difference of perfect squares can be factored. When you take the square root of x squared and the square root of 16, those are both perfect squares. So we have an x plus 4 and an x minus 4 for our factored form.